Hello. So I'm just making this video. This is a previous year question from CMI. The question says that let R is integer domain and a field F is contained in R as a subring. Okay. So now you have to show that if R is a finite dimensional vector space over F, then R is a field. Okay. So one R integer domain is given and F is contained in R. This is also given. Now, if R is a finite dimensional vector space, then you have to show that R is a field. So, okay. So before I start the question, let me recall. I mean, first thing which you have to know what is integral domain. I hope you know what integral domain is. Integral domain means if AB equal to 0, let me just write it briefly. If AB equal to 0 implies either uh, A equal to 0 or B equal to 0. And the second thing you have to know what is important condition for field. What is field? Field is basically, let's say, F plus dot E is a field, meaning F with respect to plus E and F star with respect to dot is abelian an abelian group. Okay. So these are the thing. And also let me make it in a field, every non-zero element has a multiplicative inverse. Multiplicative inverse. So these are the things which I wanted to make you recall about a field and integer domain. Now let's get to the question. So the question is said that if we assume that R is a finite dimensional vector space, then we have to show that R is a field. Okay. So let's see the solution now. So the aim is to for all R belong to R because we have to show that uh, uh, R is a field. So for all R belong to R, there exists R dash belong to R such that R times R dash equal to 1. Okay. So this is my aim to show that F is a so the R is a field. If I am able to show this that for all R belong to R, there exists R dash belong to R such that R times R dash equal to 1, then we are done. Okay. Now now how can I proceed? So from alpha, consider non-zero belong to F. Okay. Now define a map F alpha which is from R to R. Okay. This is R. So I am what I'm consider alpha not equal to 0 belong to R. Now what I'm doing, I'm defining a map from R to R, and the map is actually we can we'll think R is a vector space over F. This is how I will think it. This approximation, this mapping. And what this mapping is doing, this mapping is taking taking R to alpha R. Okay, what this map is doing? This map is taking R to alpha R. Okay, where alpha is fixed. Okay, now one can check that if alpha linear is linear transformation. How? Because one can easily see that f alpha of r1 plus r2 equal to f alpha of r1 plus f alpha of r2, and also f alpha of c times r equal to c times f alpha of r. This is very evident from the definition of the mapping. Okay, so implies that, so we got that f is a linear transformation. F is a linear transformation. Okay. Okay. So since f is a linear transformation, then we can talk about the kernel of f, right? So what is kernel? Kernel is basically all such R belong to R such that f of R equal to 0. That is, all such R belong to R such that alpha R equal to 0. Now recall that alpha was not 0, and the capital R is right, capital R is integral domain. This is very crucial. So for that reason, this this kernel f must be 0, because alpha is not 0, so R must be equal to 0, so that alpha R has to be to for that, so that alpha R equal to 0, I need that R to be 0. Okay, fine. Now I'll try to apply this rank nullity theorem. So this is another thing which I'll ask you to recall. Nullity theorem. What it says, rank f plus nullity of f equal to dimension of R. So, so also it is given that R is a finite dimensional vector space. So dimension of R is something, some natural number. Okay. Now the nullity of f is 0 from here. From is 0 implies that rank f equal to dimension of f, which implies that which implies that f is onto. And from here I can say that f is 1 1. So this is another theorem, another result of if the kernel is 0, then the function is 1 1. And this is another theorem. If the rank of f is equal to the dimension of other, then f is onto. Therefore, sorry, not f, I mean f. Sorry, this is f alpha. This is f alpha. This is f alpha. This is f alpha. F alpha. F alpha. Okay, implies f alpha from R to R is a bijection. So what does bijection means? Bijection means every element from the in from this set R, there exists an element here such that, let's say R dash such that f of R dash equal to R. Therefore, and since we are assuming that R equal to commutative ring with unity. Therefore, one is there. One belong to R. Therefore, one has a pre-image. Therefore, one has a pre-image. Implies there exists R belong to R such that f of R equal to 1, that is alpha R equal to 1, implies uh, both implies that uh, R inverse exists. So if R is there, R inverse exists, and R is not equal to 0, obviously, because or else it will be 0. Therefore, we can say that for all R belong to R, there exists R inverse belong to R such that R times R inverse equal to 1, which implies that R is a field. Thank you.